Swayam Prabha. Digital India. Educated India.
Welcome back. So, in the last lecture we just started the discussion on the 1D consolidation theory proposed by Terzaghi, and there we have we discussed about the assumptions based on that this 1D consolidation theory was established. So, those assumptions already we have discussed. Now, basically we are considering this kind of say soil deposit. So, you have sand at top and you have sand at bottom, and in between that you have the clay layer which is getting sandwiched between these two sand layers. You have the groundwater table is here. So, that the clay is or the clay deposit is completely saturated, which is one of the assumptions, right. The depth of the clay layer is 2 times HDR. So, why 2 is coming to the picture, we will be coming to that point later on, because there is something else, because I use only HDR. So, 2 HDR will be is coming into the picture to take care of something. So, that I will come to that point later on. Okay. So, Z, that is the vertical direction. So, at this interface Z is 0 and Z is continuously increasing in the vertically upward direction. Now, we are applying some stress increment delta sigma, and you have at any point along this clay deposit you can find out the excess pore water pressure due to the application of this stress increment or the pressure increment as U by gamma W. So, that is nothing but the head of the that U is the excess pore water pressure and H is the head of water due to that. So, that H you can find out by putting the piezometer at any location in the clay deposit. Okay. So, this is the problem. So, this problem we are going to say analyze. Now, we are considering any say soil element, okay, some 3-dimensional soil element we are considering in the clay deposit. So, which is having the dimensions dz in the z direction, dy in the y direction and dx in the x direction. So, dx, dy, dz is the total volume, dx into dy into dz is the total volume of this soil element. Now, we are considering 1D flow, that means the flow will be only in the one direction, as that is another assumption in the 1D consolidation theory establishment, right. So, the flow is happening. So, this is the inflow direction. So, inflow is happening on this plane. Okay. So, on this plane, so Vz into dx into dy. So, Vz is the velocity of flow or the water. Okay. So, on in the inflow on the when it is entering the soil element, and when it is exiting the soil element, at that time the velocity is Vz plus del Vz del z dz, right. So, that is the incremental velocity. Now, for the soil element, shown, okay, in this figure, okay, rate of outflow, please try to understand. So, this is completely mathematical. So, if you understand this thing, then rest of the things will be pretty I mean similar or simple, right. So, rate of outflow minus rate of inflow, that means whatever amount of water is going out and whatever amount of water is going in, okay, the difference between these two will be nothing but the rate of volume change. Am I right or not? Because the rate of inflow, whatever is entering and whatever is going out, the total quantity, if the mismatch, that mismatch is happening due to the volume change of the soil deposit, right. So, thus what is rate of outflow? The rate of outflow is nothing but Vz into del Vz del z dz into dx dy, right, on that area, on that cross sectional area dx dy the flow is happening. So, that is the quantity of outflow. What is the rate of inflow? Rate of inflow is nothing but Vz into dx into dy, that is nothing but your rate of inflow, that is the amount of water or the fluid is entering the soil element, and that is nothing but rate of volume change del V dt, okay, where V is the volume of soil element and Vz is the velocity of flow in z direction. Agreed? So, this is the expression for your fundamental 1D consolidation theory. I mean first, I mean this is the backbone equation or the expression for your 1D consolidation theory. Now, from that equation we can get del V z del z dx dy dz is equal to del V dt, where V is the volume of the soil. So, using Darcy's law I can write V z equal to k into I. Now, k is the coefficient of permeability and I is the hydraulic gradient. Now, that can be written as minus k into del h del z, because minus sign is coming because your I mean you are getting basically the height or the pore fluid, okay. That is this del h del z is nothing but your hydraulic gradient, right. So, minus sign is coming because of your pore pore pressure, right, or pore fluid pressure is coming down or it is decreasing with increase in the velocity. So, now that minus k into del h del z is equal to, in place of h you can write down u by gamma w, right. Already we have seen u by gamma w we can write in place of h, h is the head of pore water pressure. So, in place of h we can write down u by gamma w. So, if I put h is equal to u by gamma w, so I can write minus k gamma w del u del z, right. So, that is inversely proportional. So, that is why this negative sign is coming to the picture. Now, from equation 4.22 and 4.23, so from these two equations basically I can write in place of del v z del z I can write k by gamma w del to u del to z is equal to 1 by dx dy dz into del v dt, right, very simple. Now, during consolidation rate of change in volume of soil is equal to rate of change in volume of voids. Already several times we have discussed this thing. So, volume of soil whatever change is happening in the volume of soil, that is nothing but equal to the volume of change in volume of voids, right. So, if that is true, so del v dt, that is the rate of change in volume of soil, is equal to del v v by dt del t. So, which is nothing but rate of change in volume of voids, which can be written as in place of v v I can write v s plus E into v s, agreed, where v s is the volume of solid and E is the void ratio, and we can write down, so v s plus E v s is nothing but v v. So, I can write this. So, from this if we expand this term, so I can write del v s del t plus v s into del E del t plus E into del v s del t. Now, as soil solids is incompressible, so already this is one of the assumptions, we are considering the soil solids are incompressible. As the soil solids is incompressible, then basically del v s del t must be equal to 0. There will be no change in volume of solid with time. So, del v s del t must be equal to 0. If that is 0, so this term will be 0 and this term will be 0. So, this term will be left out. So, v s again we can write, we can see, or we can establish this thing from our previous background or previous knowledge, that v s is equal to v by 1 plus E naught. So, basically we can establish this relation v s is equal to v by 1 plus E naught from our previous knowledge whatever we have covered. So, which can be written as dx v. What is v? V is the volume of soil element, that is nothing but dx dy and into dz. So, that divided by 1 plus E naught. So, del v dt is equal to, so basically in place of v s, so basically del v dt is equal to del v del t is equal to v s del E del t, right. So, that is in place of, sir, del v del t is equal to v s into del E del t, right. Now, combining equation 4.24 and 4.26, okay, we will be getting minus k by gamma w del to u del to z is equal to 1 plus 1 by 1 plus E naught into del E del T, right. If you combine these two equations, you will be getting this expression. Now, the change in void ratio is caused by increase of effective stress, that is a decrease of excess pore water pressure, that also we know from our earlier discussion, right. The change in void ratio is caused by, I mean which will cause this change in void ratio, that will be basically your increase in effective stress. If you have the increment in the effective stress, then only the volume will be changing, right, otherwise there will be no change in volume, already we have seen. The volume change is completely associated with the increase or enhancement in the effective stress. So, and which will further tell you that there will be some excess pore water pressure will be going down, right. So, decrease is decrease of excess pore water pressure. So, the change in void ratio is caused by increase of effective stress, that is a decrease of excess pore water pressure, agreed. So, assuming they are linearly related, that means this change, that means change in void ratio, okay, caused by some increase in effective stress and decrease in pore water excess pore water pressure. So, these things are linearly related, okay. So, the relation between these things are linear. If that is true, then del E, that is the change in void ratio, is equal to some, say, I mean some constant A v into. So, is if effective stress increases, I mean change in void ratio will be happening. So, A v some constant into multiplied by del into delta sigma prime, right. So, that is nothing but this gives me the increase in or the change in effective stress. So, if it increases, that also will be happening. So, this is some constant, we will come to that point what is this constant, what is known as. Therefore, you have some that is equal to minus A v into del u. Why minus? Because with change, I mean enhancement in the or increase in the effective stress, you will be getting decrease in the excess pore water pressure. So, that will be, I mean inversely, I mean not inversely, that will be in the negative relation, right. So, minus A v into del u. Now, where delta sigma prime is nothing but change in effective pressure and A v is coefficient of compressibility and a constant. So, A v is known as coefficient of compressibility. So, please remember this term like C c, C s, all those things you remember. Similarly, A v you need to remember what is that is known as coefficient of compressibility, that is nothing but the change in void ratio divided by change in effective stress. So, that ratio, because you have the linear relation. So, that ratio is nothing but the coefficient of compressibility. Now, combining equations 4.27 and 4.28, now we can get. So, this was there earlier, now we can write that is minus A v into 1 plus E naught into del u del t. So, if you go back, so del E del t, in place of that we can write down this del u del t, in place of del E del t we can write down del u del t minus A v into del u del t, right. That is nothing but equal to minus m v into del u del t, where m v is the coefficient of volume compressibility and is equal to A v by 1 plus E naught. Okay. So, A v by 1 plus E naught, that is nothing but your m v, and that is known as coefficient of volume compressibility. Okay. So, therefore, we are getting one expression like this, del u del t is equal to C v into del 2 u del 2 z, okay, which is nothing but equation 4.30. So, we are getting some partial differential equation which is nothing but the 1D consolidation equation. Okay. So, del u del t is equal to C v into del 2 u del 2 z, where C v is the coefficient of consolidation and is given by k by gamma w into m v. Okay. So, please now try to understand how we have got this 1D consolidation equation, right. So, now if you try to solve this equation, what are the things you need? You need boundary conditions as well as initial condition, right. So, let us see what are the different boundary conditions and initial condition you have. So, equation 4.30 is the basic differential equation of Terzaghi 1D consolidation theory and can be solved with the following boundary and initial conditions. So, what are the different boundary and initial conditions? At z equal to 0. So, this is the first boundary condition at z equal to 0, that means you are here. Okay. What is your excess pore water pressure? That must be 0, because that is the interface between the clay and sand layer. So, the water will be draining out through the sand layer, right. So, at that location you will be having the U equal to 0, that is the excess pore water pressure must be equal to 0. Then where will be the other location where excess pore water pressure must be 0? That will be at 2 into HDR. So, Z equal to 2 HDR, your excess pore water pressure must be 0, and at T equal to 0 your excess pore water pressure was U naught, U equal to U naught, right. That means, you are just applying the increment of effective total stress, that is delta sigma, and immediately you will be observing that excess pore water pressure will be building up, right, and that is nothing but U equal to U naught. Okay. So, these are two different boundary conditions and initial condition. Now, if you apply those things and if you go back to your mathematics and if you solve this differential equation, you will be getting the solution like this. So, U equal to summation m equal to 0 to infinity plus 2 U naught by m, capital M, into sin m z by 2 HDR into e to the power minus m square T v, where m, small m is an integer, capital M is 0.5 into pi into 2 m plus 1, U naught is the initial excess pore water pressure as I told you, and T v is a time factor, that is a non dimensional term, and this time factor is equal to C v into T. What is C v? Coefficient of consolidation, already you have seen. C v into T, T is the time, divided by H d r square. Okay. So, H d r square means half of the soil deposit depth. So, that is why we had taken twice H d r, that is why we are getting this the very simple expression, like the twice H d r was the total depth of the clay deposit, now we are getting H d r at the bottom. So, that means the basically if you know T v, that means for different values of T you can establish T v by knowing H d r, right. So, if you know T v, if you know U naught, if you know all those things, you can find out the U, that is the, what is U? U is the excess pore water pressure at different time, right. So, as time increases, you can find out how your excess pore water pressure is going to build up. So, that is your main objective, right, in the or how your excess pore water pressure is getting dissipated, right. So, as you know, at T equal to 0 your excess pore water pressure must be equal to U naught, at T equal to infinity your excess pore water pressure must be equal to 0, right. So, in between that, from T equal to 0 to T equal to infinity, how the pore water pressure is getting distributed. So, that you will be getting from this expression, and once you know the excess pore water pressure dissipation or the excess pore water pressure, how that is getting distributed, based on that you can find out the effective stress distribution, because if you know the total stress, you can find out the effective stress by knowing the excess pore water pressure. So, I will stop here today. So, in the next lecture we will be talking or we will be seeing or we will be observing the excess pore water pressure distribution, and then other things we will discuss about consolidation theory in soil mechanics. Thank you very much.